Gnanam Paramam Dheyam. Knowledge is supreme.
Come back to this continuation of the last lecture. Now I will be more formal, writing definitions more precisely, etc. So, first 1 or 2 lectures I will spend on the preliminaries on fields and polynomials. So, first about the field. So, first, as we just mentioned, for the completeness, our notation is set of natural numbers n, set of integers z, set of rational numbers q, set of real numbers r, and set of complex numbers c. This was, I will assume that participants are familiar with these number systems. These I will keep referring them as number systems. So, each one of them has 2 binary operations. One is addition and the other is multiplication. And both these operations are compatible with each other. Compatible with each other. That means they satisfy so-called distributive laws. I am not going to go into the details because all the participants in this course have studied such systems. And in fact, originally they were defined for natural numbers, and then they were extended to integers, and then they were extended to rational numbers, and they were extended to real numbers, and they were extended to complex numbers. So, this was what the mathematics progressed up to 18th, 19th century. And let me note the properties here and how it has improved over time. So, for example, n with plus, this is an n with a dot, that is multiplication. These are monoids. Monoid means a binary set with a binary operation which is associative and has a neutral element. Similarly, n dot is also monoid. The neutral element for this is 0 and neutral element for this is 1. And together n plus dot, this is a number system. This is natural numbers, and these 2 operations are compatible with each other. So, z plus and z dot, together it is z plus dot, and here identity is 0, here identity is 1, identity or neutral element. I will keep interchanging the words. So here it is better now, with this Z plus is not only a monoid but it is a group. It is an abelian group in fact. Abelian means it is commutative. These operations are also commutative. All the operations in our number systems are commutative. Z dot, it is not a group, but it is just a monoid. Monoid, not a group. So because it is not a group, we have a problem in solving such equations. This is a linear equation, coefficients are in Z, but the solution is not integer solution, solution is minus half. So you cannot divide by 2. 2 doesn't have inverse with respect to multiplication. That is why this equation doesn't have a solution in Z. So not only we need to be precise to say where the coefficients are, but also we need to be precise to ask questions, where are we looking for solutions. If you are looking for solutions in Z, this equation doesn't have a solution in Z. So with this kind of problem, rational number is better. So Q plus and dot, this together now, both Q plus and obviously Q, and you have to remove 0 because 0 doesn't have inverse with respect to the multiplication. So that I will denote by Q cross dot, where Q cross is remove 0 from Q. Both these are abelian groups. So then the linear equation now, if I take any linear equation like this, Ax plus b equal to 0, the solution makes sense. Linear, therefore A cannot be 0. Then the solution is minus b by A. And even if A and b are rationals, b by A is also rational number. So therefore a linear equation over Q has a solution. Similar thing will work for real numbers and complex numbers. Real numbers and complex numbers. So such a thing is called a field. Such a thing is called a field. So what is the formal definition? Field. Field is a set K. It has a 2 binary operation plus and multiplication. With respect to plus, it is abelian group. Abelian means commutative. Abelian and same thing as commutative. Abel was the first to consider such an operation, so it is usually called abelian. It is named after abelian. And remove 0, the additive identity for K. So 0 and 1 are usually denoted by, depending on the context, they are not, of course this 0 and 1 is also notation for the complex natural numbers, but in this context now 0 is the neutral element or identity element with respect to the binary operation plus, and 1 is a neutral element with respect to the operation multiplication. Also the word used, multiplication, is used because of the standard examples. So K minus 0 with dot, this is also an abelian group. And of course the operations are compatible. Compatible just means they are connected by the distributive law, that is, let me write at least once, A times B plus C equal to AB plus AC for all A, B, C in the field. Okay. And obviously the other side also, but I will not write other side because now our operations are commutative, so we don't need to. But if you are studying non-commutative ring theory or some such subject, then we need to mention that. So this is called a distributive law. And of course, I didn't associativity is also there for this individually, that comes under the fact that it is a group. So this allows us to calculate, simplify the formulas and calculate it. So this is very important, because if this was not there, then different people will get different answers and the world will not be compatible with each other. So these are very important part of the definitions. So such a thing is called a field. The examples of fields are Q with the natural addition and natural multiplication. This is a field. Therefore, this is called a field of rational numbers. Field of rational numbers. With the similar thing, one would call this Z plus dot. This is a ring of integers. It is not a field, but it is a ring. And now what should be ring? Ring, only condition you drop is with respect to plus, with respect to the multiplication. It may not be a group, but it is certainly a monoid. Such a thing is called a ring, a commutative ring. One doesn't say abelian group or abelian field, one calls it a commutative ring. So in general, we have a concept of commutative ring. That is a ring, the set R, which has two binary operations, and R plus is abelian group, and if you remove identity for plus, that is denoted by 0 with respect to this, this is a commutative monoid. That means it has identity neutral element with respect to this. A typical example of a commutative ring is the ring of integers. Some more examples of field: real numbers with usual addition and multiplication, that is a field of real numbers. I will not dare to define this in this course. I will assume that all of you know how do you construct field of real numbers from the field of rational numbers. I will only say that you need a concept of limit. So what was roughly was, if you try to see rational numbers, it had gaps, and if one wants to fill up the gaps and try to draw a picture of real line like this, this is a picture of real line. There is somewhere 0 here, 1 here, and this side is a minus side, and so on. So usually the convention, standard convention which inherited to us from physics was, when you go on the left side it is negative, when you go on to the right side it is positive. And this is also related to our Indian philosophy, mythology, that when you go on the right side it is more positive. Okay. So that is field of real numbers. And one more example, C plus, complex numbers plus dot. This is the field of complex numbers. So again, if one looks at the historical perspective, uh, till Steinites, uh, people were not very clear about complex numbers. But after Steinite's paper came, many things became more and more clearer. And for example, I will just mention here that just mention, but we will prove it sometime later. This complex one of the construction that Cauchy gave was of complex numbers was if you take the polynomials. So this I will polynomials in one variable x with coefficients in real numbers, and you go modulo the polynomial x square plus 1. This is still not very clear, but I will make it soon clear. This quotient ring is a field, and that field is called complex numbers, and there you see then every complex number z can be uniquely written as a plus ib, where a, b are real numbers and I is a complex imaginary complex number which is the square root of minus 1. See, writing this is not very good, it is real sloppy, so I want to improve all this. So first of all, one has to explain what is the polynomial ring and how do I write this and so on. But this soon I will do it. This is Cauchy's construction of complex numbers. So you see, in this hierarchy, Q, R and C, these are fields, and one also say that this Q is a subfield of real numbers, subfield. Means the binary operations are same and Q is in its own right a field. Similarly, R is a subfield of complex numbers. In this hierarchy, up to Q, definition of Q from natural numbers is not too bad. It is algebraic definition only, because from n to z you provide negative numbers, and from z to q you provide fractions. So here you provide negatives and here you provide fractions, and this is also not so bad. This is also easy. If you want, this is a vector space of dimension 2. 1 and I is a basis, that is one explanation, and or this explanation is also algebraic. But here it's a big gap, and this is without limit one cannot do this. So definition of real numbers is more complicated than one thinks. But on the other hand it is a very real practical definition. So one, okay, now more examples of fields, and also I want to make this clear. So before I go on, so how can one construct more fields? There are two ways. Or how do you construct more rings? So from you can ask more examples of fields. Or rings. And usually nowadays there are at every stage there are courses like rings, group rings and fields. So more and more examples, and it is more appropriate to construct examples from the given examples. And now the only examples we have are this N, Z, Q, R, C. So from these I will construct more examples of rings as well as fields. So the only example of a ring so far, of course, all these Q, R, C also they are rings. So but the first ring is a ring of integers Z. From this I am going to construct many rings. So given any integer n, any natural number n, in fact n bigger equal to 1, I am going to define an equivalence relation on the set Z, equivalence relation, on Z, which will be denoted by these two equal symbols together and suffix n here. But I will drop this n and fix our n, so I will just write this. And this symbol is very important. This was introduced by Gauss, and that created a revolution at that time in the simplification of notation. So what is it? So we will say that if a and b are integers, a, read also, a congruent to b mod n. This means, so this is the definition. N divides b minus a. Divides. This is a symbol for divides. Or in other words, b minus a is a multiple of n. So it is c times n. So we have a relation on the integers, and I want to check that this is an equivalence relation. This is an equivalence relation on Z. So what should we check? We should check that it is reflexive, symmetric, and transitive. These three things together, it is called an equivalence relation. And I will leave it for you to check that this is an equivalence relation. So I will just mention here check this. Once you have an equivalence relation, we can talk about the equivalence classes and quotient set. So equivalence classes, that means given any a in integers, we are collecting all the elements which are equivalent to a under this. So this is by definition all those integers b in Z such that a is congruent to b mod n. And we know then these are the equivalence classes, and we know that the equivalence classes either they are disjoint or they are equal. And then the quotient set, that is usually denoted by Z modulo this. And this has obviously how many elements? This has precisely n elements. Namely, they are equivalence classes of 0, 1, etc. up to n minus 1. These are precisely the integers. When I divide by n, I get 0. These are precisely the integers. When I divide by n, remainder is 1, and so on. So on the quotient, so these are also denoted by, so we will usually denote these equivalence classes Z, this, instead of writing this, one writes Z suffix n and read it Z modulo n. And the elements of this, instead of writing the bracket, square bracket 0, square bracket 1, etc., we will write 0 bar, 1 bar, etc., etc., n minus 1 bar. And now I want to say that the binary operations from Z, namely the natural addition and multiplication, they will induce a binary operations on this new set. and they are denoted by this. And how are they defined? Obviously, it's a natural. So, you take, for example, A bar plus B bar under this operation is by definition. You add A and B as usual and take their bar. Taking a bar means taking a remainder. Similarly with the multiplication. AB and bar. Now it is easy to check. I will only write here check that Z modulo n with these operations is a commutative ring. So, we have many rings now, as many as natural numbers we have many commutative rings. So, I will not check this. Moreover, I will also mention here, this is an important observation. If I take a prime number P, P is prime number, this P is called the set of prime numbers. So, P is considered as subset of n. And what is the prime number? Those natural numbers whose only divisors are 1 and itself. These are called prime number. Only divisors are 1 and itself. Again, when I say only divisors, that means I am only taking divisors in natural number. Those are called prime numbers, and it is now very important topic to study prime numbers. How they are, how many they are, how often, what is their distribution and so on. This is a very big subject, very important subject nowadays. It is called number theory. Number theory, study the prime numbers, study of prime numbers. So, anyway, so Z modulo n, this is a field if and only if n is a prime number. This is very important observation, and I want you to check this. So, that way we get lots of examples of fields. We know that they are the set of prime numbers is infinite. This is a famous proof by Euclid, that if there were only finitely many primes p1 to pn, then look at their product and add 1, and we know that this is again a natural number, and we know that next time I will recall this precisely what I want to recall, that this again a natural number. So, it has a prime factor, and that prime factor cannot be one of the p1 to pn. Therefore, you get a new prime factor. That is why that's a contradiction. So, this was a Euclid's proof that P is an infinite set. So, we have now infinite examples of fields. The only difference between the earlier fields and these fields, all these fields are finite fields. Finite means the underlying sets are finite sets. In the other examples Q, R and C, they were all infinite sets. So, next time I will want to still give more examples of rings, and then we will start studying polynomials over field, and then we will set up our dictionary correctly. What does one mean by solutions, what does one mean by polynomials and so on. Thank you.